Welcome to this advanced discussion about what I call the IMC Safety Speed. This is where I want to spend a little bit of time talking about some of the technical details of the IMC Safety Speed. I will generally direct my comments towards those who are certified pilots in terms of the verbiage that I will use. However, I expect that air traffic controllers who are not pilot rated should have no trouble following along with this. The primary mission behind this is just to kind of knock off some of the technical details about this IMC Safety Speed, address what might be some potential concerns that some people might have about it, to dispel a couple of myths that I've recognized might exist about something like that based on conversations I've had with real-world pilots. For the record, I'm filming this on December 14th of 2020. Also, for the record, this is not a fancy PowerPoint discussion. In fact, what I've done as far as the PowerPoint behind the video here is I've literally just attached that opening slide to what had been the Foundational Ground School video number 404, because I want to start by kind of reminding you about a couple things I talked about in Foundational Ground School video 404. I'm going to skip the gliding variability part and the last thing about paging pilot-rated controllers, and just by way of brief refresher, remind you about the middle two concepts, the VFR-in-IMC family of emergencies and introducing the VG diagram. And for our purposes, I am not going to be in presentation mode. I'll just be in editing mode as I kind of go through that. So let me just put it about here. And just by way of quick refresher, when I think about the VFR-in-IMC family of emergencies, I think about these kinds of categories. The three I want to particularly focus on are the VFR-in-IMC, where the pilot does not have a meaningful horizon reference at the time, whether they're technically IMC or one of these low visibility VMC situations, such as happened to JFK Jr. back in 1999. There's also the person who's stuck above an overcast cloud layer, and so they present to us air traffic controllers while VMC. And then number three is kind of the VFR underneath IMC, scud running type situations, typically low visibility. Can kind of see the ground perhaps. That might be a bit iffy, so that will have some variability. And these scud running type situations are going to be nasty because sometimes we really are facing two threats at once. We don't really know if they have a good horizon reference and so on. So there's going to be a fair amount of confusion. And this one, because there's two threats, one is possible loss of bank control and going thunk into the ground before you actually rip the wings off. Versus just hitting things that are terrain or attached to terrain, and so it's a CFIT, a controlled flight into terrain issue, makes this one a little bit tricky. So we'll kind of cover some of these as it relates to the IFR safety speed, because that's going to have some different situations. All right. I then very briefly introduced the VG diagram. Again, pilots should be familiar with this. The way I presented it in Foundational Ground School video 404 sort of introduced it for non-pilot rated controllers. And then I took it in a slightly more advanced way and sort of built my own. So I had the 1G line. I put a yellow line at 3.8 Gs, which is where normal category aircraft are certified to. Utility category aircraft are certified at 4.4. And so for all intents and purposes, even though the yellow line, where in principle you start bending important things like wing spars, is at 3.8, because it can be normal or utility category, and they kind of bracket 4Gs, and 4Gs is by physical definition double the stall speed. If I say go to the next slide, where I'm putting the stall speed for some arbitrary airplane at 50 knots, then the maneuvering speed is essentially double that. So I'm just going to think in terms of whatever the stall speed is, that maneuvering speed is technically not exactly double that, but effectively it is double that. The red line is an additional 50% where you actually start breaking things like wings and tails off the airplane and so on. That maneuvering speed does vary with weight. That was kind of the point of this slide here. And it's because the stall speed varies with weight. And so what I did in a subsequent slide is I asked you to kind of think about the airspeed, not in terms of knots or miles per hour or something, but almost as a percentage of the maneuvering speed. And even though the arrow is pointing slightly off from the 100% line, I'm using this as basically 100% of maneuvering speed for any particular airplane at a given point in time, which has a particular weight. And so stall speed is, again, for all intents and purposes, 1/2 of that. Once we sort of define that, on the next slide I pointed out that a variety of airplanes cruise at speeds expressed as a function of the percentage of maneuvering speed, anywhere from about 100% up to about 140%. When I was deciding what I wanted to cover in this video, I briefly considered going through and giving you some representative examples and actually looking at performance charts for, say, cruise performance for a 172S, 8,000 feet, standard temperature. I wouldn't run it at quite 77% of max continuous power, so I might run an airplane like this at 72%. That gets you 122 knots. Take you to a free online E6B, because that's all our favorites. That gets you to, it says indicated that really should be calibrated 108. Go back in and sort of check all the boxes. So if you're at 108 calibrated, what is that going to be? An indicated on a 172S. We'll back it down by 3, okay? So that gets you to 105, which happens to be. So a 172 at gross weight, a 172S at gross weight, is actually cruising right at 100% of maneuvering speed. Okay, however, if you're flying it at less weight, stall speed drops, maneuvering speed drops. Meantime, if anything, as you drop the weight, the airplane might just pick up 1 or 2 knots. It's nothing meaningful, but technically, if anything, it picks up speed. And so a 172 at gross weight, under those kinds of cruise conditions, might be cruising at 100% of maneuvering speed. At lighter weights, it might be up to 110 or 120. I haven't crunched the numbers. So there's some variability, even though I'm kind of doing that there. And I floated the idea that the reason for noticing this is that whatever that cruise speed is expressed as a function of maneuvering speed, if somebody gets into a graveyard spiral, they pick up speed, they have their oh shit moment, and they break the airplane. And so the basic concept is just to get pilots to slow down. And so what I want to do is talk a little bit more about the technical side of this, just to kind of cover this slightly, partly for legal purposes, just so I don't get accused of ignoring important things. And we will learn a couple small things along the way that are relevant for us. But then what I want to do is kind of cycle back and go back to thinking in terms of those top 3 VFR and IMC kinds of situations, and think about how we would get a pilot to do this and when specifically we would get a pilot to do this. Let me start to address that this way. So I'm going to go back to the PDFs here, and I'm going to start with the point 65. There are 3 sections that deal with how we as controllers should be helping VFR pilots who get into IMC. 10-2-7, 10-2-8, 10-2-9. As I argue in a separate video, I think that these 3 sections have major problems. I have definite substantive objections to them. This video is not the place to discuss those. The one I want to focus on at the moment is just 10-2-9, which is a section officially labeled Radar Assistance Techniques, and it says, use the following techniques to the extent possible when you provide radar assistance to a pilot not qualified to operate in IFR conditions. And at the moment, for purposes of this video, the only one I'm concerned with is paragraph C, which says have pilot lower gear and slow aircraft to approach speed while in VFR conditions. So in principle, I'm absolutely on board with this, but let me note a couple things. First of all, for what it's worth, and this is not a big deal, this has nothing to do with whether we have the airplane on radar or not, even though 10-2-9 is about radar assistance techniques, and it's talking about when you provide radar assistance. What if we get a VFR and IMC situation on a non-transponder equipped airplane? So the pilot calls us on the radio, says, hey, I'm VFR, I'm not instrument rated, I'm in IMC, I need some help here, I'm declaring an emergency. Does this mean that this is only applied if we have radar contact with the air? It has nothing to do with radar, so ignore that part of it. Again, that's not a big substantive thing, that's just more in the kind of stupid category if I'm blunt about it. But the principle is, let's think about C for a second on its own merits. Have pilot lower gear. Let me just pause there. Absolutely. If it's a retractable gear airplane, lower the gear. It adds drag, doesn't change the trim characteristics of the airplane. If the pilot begins to get into a graveyard spiral, because there's more drag, it will slow the amount by which the airplane accelerates, and that is a good thing. So that's non-controversial. And in fact, just in terms of lowering the gear, I would do that in a heartbeat as a controller talking to a pilot in one of these situations. I don't care if they're VFR or IFR. When we have them do it, we get in those situations, it wouldn't be the first thing I would do, but relatively early on, I would recommend gear down. Now, if we're concerned about icing and that's going to add drag on the airframe, that can be different and so on. But essentially, I don't care about whether they're VFR or IFR when we have them lower to the gear. Let's just pause on that for a second, even before we get to the slowing down part. Let's think about something that's a head scratcher on paragraph C here, and that is this. Let's just focusing on the gear. Have the pilot lower the gear while in VFR conditions. Well, the whole point is that this pilot is not in VFR conditions. So just get your head, square that circle, get your head around that for a second. Now, in principle, absolutely agreed. So implicitly what this is kind of getting at, and let me put it this way. Let's just suppose you have a controller who's looking at this for the first time there in their early developmental period with the FAA, and they're trying to really make sure they understand this at some deep level rather than just by rote. And they're thinking, okay, so I got a pilot who's in IMC, but we can only have them do this when they're in VMC? And besides, I guess presumably they have to land sometime, so eventually they're going to have to slow to approach speed, for the approach at some point. What if we never get them to VFR conditions? Can we not do that? I guess this is a suggestion because it does say to the extent possible, but what's the deal here? So the slowing aircraft is part of what I'm talking about in terms of getting an airplane slowed from whatever the cruise speed is down towards what I'm calling the IMC safety speed, which is somewhere ballpark in here. Okay, but the basic idea, so I'm on board absolutely with slowing aircraft, and I would prefer to do it in VFR conditions, but that's not always the case. So with this in mind, whether it's slow aircraft to approach speed or what I'm calling that proposed IMC safety speed, let's think about when we would do this, expressed as kind of a function of those three categories of emergencies. Here, they're in IMC, and unless we can maybe get them to a break, where they're temporarily VMC, let's just say that they stay IMC or they get into, a JFK Jr. low visibility situation where they're out over the ocean for a while and it's just murky and it's technically VMC, but it's the low visibility thing. When would we get them slowed down to what the .65 calls approach speed, or what I'm calling the proposed IMC safety speed? So I'll kind of get back to that in a minute. If they present to us kind of above an overcast layer, they're VMC when they present to us. It is super easy to do it fairly early. I would get this done fairly early in the situation for a variety of reasons. The scud running situation, again, man, these are nasty. I'm going to suggest that we will typically go to these fairly early unless it is thought that the best strategy is just to climb them up. As I mentioned in Ground School Video 4, sometimes the preferred strategy when we get to the scud running situation, when it's presented to us, where we're dealing with two threats, is it's best just to climb. So, for example, as long as the clouds right above where this person is scud running are not laden with ice, let's say, okay, if we have them climb, we go from two threats to one threat. So in the kind of the textbook example of this would be if somebody's sort of scud running in its area where it's kind of rolling hills and there's definitely cell phone towers out there, you have a lot of threats as far as CFIT type stuff. So you have a lot of, running into things type threat. And if the clouds do not have ice, that one's real simple. Climb. By the way, the helicopter safety community, they are very big on, and again, keep in mind earlier in 2020, which is the year, of course, in which I'm filming this, we had the Kobe Bryant helicopter IMC crash out in Calabasas, California. But regardless of Kobe Bryant, the helicopter safety community is very big on the 3 C's. Climb, call, confess. In other words, if you get a helicopter into this inadvertent IMC, and the helicopters tend to get into some of these kind of scud running situations, and at some level that's what happened to Kobe Bryant, just go ahead and do a straight climb. Yes, that puts you in the clouds. Then call ATC and confess what you're doing. But at some level, the fundamental aerodynamic or physical thing that's going on is go ahead and convert it from the dangerous scud running thing where you have two threats and climb to where you just have the one threat and go from there. I am absolutely 110% on board with that helicopter concept of climb, call, confess. For our purposes as controllers, I'm thinking a bit more in terms of fixed wing airplanes here. If we do have a helicopter in one of these scud running situations, again, it might be very good just to keep them flying straight, keep them flying fast. You heard me right if you're not familiar with helicopter IFR flight. and have them climb and convert them into this situation, because this is far easier. Quickly on helicopters, although my focus is not primarily on helicopters, us non-helicopter pilots think that in an emergency, helicopters can just slow down. Not if you talk to somebody who knows what they're talking about helicopters. Helicopters at speed are fairly stable. Helicopters at slow speeds are very unstable. If you don't believe me, try hovering a helicopter. You think, oh, it's slow speed, it's got to be easy, right? No, the slower you go, the tougher it is. One of the worst things you can do in a helicopter when you're scud running is start slowing down too much, and now you really have your hands full. But let's get off of the helicopter theme for a second. Anyway, so in IMC, the safety speed I'm proposing is better, but there's a question about when we would go to it. Under this one, number 2, VFR above IMC, yeah, go to it fairly early. Number 3, it kind of depends. We're either going to adopt that kind of climb strategy, but if for whatever reason that climb strategy is not the way that it seems good to go, either that strikes us as bad, or really it's up to the pilot, but the pilot is, no, I'm not climbing, I'm going to kind of stay down here and fight this for a while, then we want to go to it fairly early. I will develop that particular theme a little bit later in this video. So with that in mind, let's kind of switch gears. I'm going to come out of the PowerPoint. We're going to spend a little bit of time kind of in PDF and also some stuff on the internet. So the basic principle is we do want to slow them to what the .65 is calling approach speed. I prefer to think of it as this IMC safety speed, which by chance happens to be about the top of the white arc speed for a wide variety of aircraft. Again, when I was thinking about what I wanted to cover in this video, I had pulled up some POHs from older and newer 172s, from older and newer Cirrus SR-22s, and so on. Decided at the end I'm not actually going to do that, and so on, but I very easily could, for a variety of aircraft, show you that it's really more by chance than anything else that the top of the white arc, which has to do with the full flap operating range, if I just grab the verbiage here from the newer SR-22 POH, that in this airplane, the 110 speed, okay, is going to be the speed that we want. That is something a bit slower than the maneuvering speed, okay, properly expressed as a function of calibrated airspeed, although you can think of it in terms of indicated airspeed, which is going to be a couple knots off in most airplanes, but that doesn't particularly concern us. One other point we're here, I'm just going to knock this one out of the way very quick as we convert to something that's on Wikipedia just for illustration, not because it's determinative, is you might remember, if your memory's good and if you were looking at this, when I went through some of the pictures illustrating how the top of the white arc happens to be for a variety of aircraft right about the sweet spot where we want it. I showed you this photo from a 172 cockpit instrument panel in the flight sim, where maneuvering speed, it just says maneuvering speed. I then showed you a Diamond DA40 TDI, and maneuvering speed it showed was VA, and this is probably what a lot of pilots think of in terms of the maneuvering speed is VA, and I kind of casually said that when we were looking at the picture from an SR-22, it was VO, not VA. Let me just knock out this minor technical difference about VA, VO, because there is a minor difference. It does not in any way affect the principle that we're talking about here, so I'm going to do it this way. Go back to PDF. We're just going to knock this one out for a moment. And let me go back to the section on load factors. When I first introduced this, we spent a little bit of time looking at some of the stuff in here. I'm not going to recover, or cover again, I should say. Load factors and stalling speeds over here on page 5-34. I'll just very briefly mention this. Any aircraft within the limits of its structure may be stalled at any speed. Now, in one sense, let me just kind of simplify that. Any aircraft can be stalled at any speed. Boom, done. Okay. Now, the thing is, if you are going too fast, you're going to overload the structure. So at some level, this is absolutely the better way to put it. Any aircraft within the limits of its structure may be stalled at any speed. Okay. And then it talks about what a stall is. Pilots know that, and so on. Now, the maximum speed at which an airplane may be stalled safely is now determined for all new designs, as opposed to the older ones, from before. And this is known as design maneuvering speed, or what's technically VA. This is different than VO. So VA is technically design maneuvering speed. It's the speed below which you can move, and I want to be precise here, you can move a single flight control one time, so you can't be going back and forth, to its full deflection for one axis of airplane rotation only. So pick pitch, roll, or yaw, in smooth air without risk of damage to the airplane. And that seems like the lawyers had a field day with that sentence, but let's just pick it apart. If you take the stick or the yoke, and let's say you suddenly go full back elevator, full right aileron, full left rudder, you now have 3 axes going on at once and so on. Now, even though you are below maneuvering speed, you can still overstress the structure because you have a very complicated thing going on. If you do just one axis and you're doing it repeatedly, so let's just say you're taking the aileron and you're going full scale back, left, right, left, right, left, right, as fast as you can. Again, you can damage the airplane even if you're below maneuvering speed, and even if you're just doing one axis and just kind of one move and so on. If it's in particularly gusty air, you can also damage the airplane, although that one might be controversial because really it only occurs if you're kind of close to VA and the gust in effect kind of puts you over VA temporarily type situation. But the point is, the lawyers have to be precise, and that's fine, and you'll actually see an example of that in a couple of minutes. But essentially, for all intents and purposes, VA is the speed that we typically think of in terms of pitch, not per se the other axes. And as long as you're below VA, you basically cannot break the airplane. You'll see an exception to that killed a number of people not too long ago. But anyway, operating at or below design maneuvering speed does not provide structural protection against multiple full control inputs in any one axis or full control inputs in more than one axis at the same time. So that's just expressing what I was talking about there a little bit differently. Now, load factors and flight maneuvers. Full application of pitch, roll, or yaw control should be confined to speeds below the maneuvering speed. Avoid rapid and large alternating control inputs, especially in combination with large changes in pitch, roll, or yaw, as they may result in structural failures at any speed, including if you are below VA. Again, kind of saying the same thing, and I'll give you a very concrete and sad example of that in just a minute. However, even before we start thinking about this, notice for any of these VFR-in-IMC kinds of situations, including the partial panel thing, which I'm not really focusing on here in this video, we do not want pilots doing full application of controls anyway. My concern, this is more of an insurance policy. So our primary strategy is keeping pilots out from the graveyard spiral, and that is primarily done by keeping the bank angle under control. And so this IMC safety speed is more of a second level insurance policy kind of a thing, so that if, and we want to avoid this in the first place, but if the pilot gets into a graveyard spiral situation and then has their oh shit moment, I'm more concerned with kind of the rapid full deflection just in pitch. And that's the way VA is typically thought of, even though you have these other things with the multiple applications and so on, or multiple axes. Okay, that's all the setup for the VG diagram, and again, I went through. We'll come back to the next page here in a minute where it talks about radius of turn, but that's going to be a specialized situation that we'll deal with a little bit later. So let's do this. I'm going to go over to the web browser and ignore the E6B where I was crunching numbers earlier as if I was trying to think through how to demonstrate very precisely the proposed IMC safety speed and the typical cruise speed as a function of the maneuvering speed. So let's start with Wikipedia about maneuvering speed. Not that the FAA doesn't have good stuff about maneuvering speed, but there's just a couple things here in the Wikipedia article that make it useful for our purposes. So I'm going to kind of come down to design maneuvering speed, VA, and contrast it with the maximum operating maneuvering speed, or VO, just to kind of knock out this technical difference. So VA, the design maneuvering speed, it is a calibrated airspeed. I did talk about that in video number 4. Maneuvering speed cannot be slower than VS times the square root of N. It does talk down here. VS is just stall speed. N is the maximum allowed positive load factor. Officially 3.8 for normal category aircraft, officially 4.4 for utility category aircraft. I'm going to simplify it, just call it essentially 4. So even though I'm not technically correct, if N is typically going to be 4 for general aviation aircraft, the square root of that is 2. So effectively, maneuvering speed cannot be slower than the stall speed, or twice the stall speed here, and need not be greater than the design cruise speed. Again, I'm not so concerned with that. What this is saying, and I'm kind of unpacking this a little bit, maneuvering speed essentially is double the stall speed at a given weight, and here's the actual way you would adjust it when the weights change and so on. Okay, if VA is chosen by the manufacturer to be, and I'm going to convert this to double the stall speed, then the aircraft will stall in a nose-up pitching maneuver before the structure is subjected to its limiting aerodynamic load. However, if it's selected to be greater than that, the structure is going to be subjected to loads which exceed, and that's why for certification reasons, VA is and again, it's the correct version of this rather than the simplified version that I'm going to use, double the stall speed. Okay, so VA is essentially in calibrated airspeed, double the stall speed. So what's VO? Well, some aircraft have a maximum operating maneuvering speed of VO instead of VA. This is a different concept than design maneuvering speed. The concept of maximum operating maneuvering speed was introduced to the U.S. Type Certification Standards Flight Aircraft in 1993, and the maximum operating maneuvering speed is selected by the aircraft designer. So the aircraft designer, in effect, gets more of a pick here, but it cannot be more than VA, okay, and then it defines the VS stall and the N as the maximum allowed load factor. In other words, VO is a different certification thing that's a bit newer, okay, and it gets selected by the aircraft designer, but it can't be higher than VA. Well, that's all true, but here's the thing. For all intents and purposes, and I've not exhaustively checked this, but it's in the interest of manufacturers to have VO pretty much be equal to VA, and if not, be very slightly underneath it. So for all intents and purposes, and for our purposes, yes, VO is technically different than VA, but in the real world, VO and VA are essentially the same. VO might be selected by the aircraft designer at a slightly slower speed. One other thing I'm going to knock out real quick. You'll notice in this Wikipedia article about maneuvering speed, there's a C also about American Airlines Flight 587, which I've already got queued up. For those who are not familiar with this accident involving an Airbus 300 that killed all 260 people on board, here's what happened. First of all, this was literally just 2 months after 9/11, and this was a crash on an airplane that had just taken off from JFK, and so there were, as this is going to say, initial terrorism concerns. I remember when I heard the news of this 2 months after 9/11, I immediately thought, uh-oh, this is like 9/11 Part 2 or something like that. It actually had nothing to do with 9/11 terrorism type stuff. The short version is this. Just after takeoff, they got into a little bit of wake turbulence from a 747 that had taken off a couple of minutes earlier. Now, this was not a wake turbulence flip, but the airplane did get jostled around. And again, this is the simplified version. I'll put it to you this way. According to the NTSB, the aggressive use of the rudder controls by the first officer stressed the vertical stabilizer until it literally snapped off of the aircraft and so on. So I'm not going to focus on it in particular detail, but what happens is when they got into some of that wake turbulence, okay, what they did was the first officer alternated between moving the rudder from the left or from the right to the left and back again in quick succession. And if you remember the way it's worded here in the Pilot's Handbook of Aeronautical Knowledge about avoiding, the one-time type thing is related to VA, what ultimately at some level happened was the first officer was going back and forth full-scale deflection pretty much on the rudder, and that's what overstressed the tail. And so partly because of that, that's why VO in effect can be a bit slower, but for all intents and purposes, I'm not focusing on that kind of stuff. So I'm not flippant when I say VO and VA are the same thing, but for all intents and purposes, for the purposes of what we're talking about for VFR and IMC discussions, it has absolutely no bearing on it whatsoever. Okay. So here's how you would slow the airplane down. So let me go back to just the 0.65, okay, and kind of keep in mind, first of all, the pilot who's stuck on top of the overcast. How do you control speed? Effectively with pitch trim. Officially, speed's always going to be a combination of pitch and power in any particular configuration as far as flaps and weight and the rest. Okay, but the basic idea is it's pretty simple. Just have somebody slow down. And the way I would do it if I was talking to the pilot, I would just first have a quick conversation with them. Okay, and so again, I'll kind of express this as if we're talking to a pilot of a modern 172 and so on. And let me go very quickly, just for purposes of discussion, to Section 2, which is going to have operating limitations. And I want to focus on airspeed limitations, and it's going to talk about, say, the airspeed indicator markings, including the markings for the different arcs. Okay, so somebody's going to be cruising along. They get into this situation, and who knows exactly what speed they're at. I'm kind of guessing they're somewhere about 100, 110 indicated when they call us in this situation. And when we are trying to get them to slow down above, okay, it's pretty simple because they're VMC. So I would first just say, safety experts recommend that you slow the airplane down. Okay, what is the top of the white arc speed for your airplane? In this particular airplane, the pilot just has to look at it and says, well, it's going to be 85 knots. As the controller, I would just say, are you comfortable flying the airplane at 85 knots? Because that is actually the speed. Leave your flaps up, but that's actually the safest speed to fly, okay, for a VFR-in-IMC situation. Pilots should have no particular reason to object. Of course, they're PIC, so if they object, that's fine. They're PIC, they're in charge, that's their decision, that's fine. But as long as they say they're comfortable flying at that speed, okay, fine. So just slowly reduce power and add some nose-up pitch trim and just trim for 85 knots. And that's the simple way to get them to there. And then they're trimmed for that speed, and that is the speed they'll stay at, although they might move around a little bit with a little bit of turbulence or, you know, some temporary phugoid action with power changes and the like, okay? And so we've gotten them to that speed. So that's how to do it if they're up above. So they're VMC when it happens. For the VFR-in-IMC, okay, what I would do in part is early on, and I would do this anyway, regardless of what we're going to do with the speed. So if somebody's kind of maybe potentially in and out of the cloud, so this isn't really a JFK Jr. situation, I would ask them something like, you know, if you get into VMC even temporarily, let us know. And for the sake of discussion, let's say somebody breaks out of the clouds and, hey, I just popped out. It looks like I'll be going back in a minute. Okay, maybe there's that window of opportunity where we can slow them down in VFR conditions. And whether you're going to think in terms of slowing them to approach speed or you're going to slow them to what I think of as the top of the white arc, either way, what we're talking about doing is, again, a combination of power and really what's pitch trim to get them slowed. If they stay in IMC, okay, I would just wait a little bit more and keep the emphasis on keeping the wings level and controlling the bank. But when there is an opportunity and things have calmed down after a couple of minutes, okay, then we would talk about trying to slowly get back to that IMC safety speed. And it's the same kind of conversation that I talked about here a minute ago. Okay, what is the speed that is the top of the white arc for your airplane? Again, using this example, this pilot's going to say 85 knots. In one of the current versions of the Cirrus SR-22, just to pull that up for a different example, the top of the white arc is going to be 110 knots because that is the 100% flap indicated airspeed limitation. So they're going to say 110 knots for the pilot flying this SR-22. Okay, are you comfortable flying the airplane at 110 knots? That's the speed that experts recommend as the safety speed for this kind of situation. And again, assuming that the pilot says yes, the way you physically achieve that speed is going to be really through pitch trim, but if you only do pitch trim, they're going to end up climbing at the higher power setting they're using for the higher cruise. So in the real world, you just slowly back the power down a little bit, slowly bring some nose-up pitch trim, and just kind of work your way back to 110 knots-ish. It doesn't have to be exact. Okay. By the way, you'll notice that the way it's phrased in the .65 is approach speed. Well, I'm thinking of it in terms of something else, but what are we doing? We're getting them to what's really an approach speed. Okay, and among other benefits, if we're going to use this all the way down through something like an approach, at the top of the white arc speed, plus or minus a little bit, well, if you're a little bit above that, you can still put down the first notch of flaps. Now, this happens to be for the modern SR-22 at 150 for the first notch, but for any airplane, you can put the first notch of flaps down at a higher speed. So even if you're, this plus or minus a couple and it happens to be plus, you can still put the first notch of flaps down for something like an approach without any problem. So that's another advantage to going to this, although that's not the primary advantage. The primary reason is this insurance policy against the graveyard spiral effects and so on. Okay, so that's kind of what you do. You can go to it fairly early for this situation. This one you want to take a little bit more time. For the scud running situation, again, just to refresh, I said if you can, you might well adopt the climb strategy, but if you can't or the pilot doesn't want to, and so you're kind of stuck down here in this scud running situation, what about this? First of all, is it beneficial? And second, what about the timing? Okay, the timing is going to be somewhat early. Okay, here they may or may not be kind of in this murky sort of half VFR, kind of marginal VFR, kind of crappy visibility and so on. It's fairly easy to get to because, again, you just gently back down the power, gently add some nose up hitch trim, and just kind of work your way down to that speed. So you can get into this relatively early. You can't go to it quite as easily or quite as early as you would for this situation, but because you are worried about running into things on the ground, you want to get to this. Now, why do I want to get the airplane slowed down? And there is a fair concern that should be addressed, and I want to address this one head on in a minute. I have talked to people about this proposed IMC safety speed in different situations, and I've had some people kind of scratch their heads and go, I'm not so sure about the scud running situation, because for scud running, I can conceive of a situation where somebody's flying along and suddenly they see the blinking light bulb on a cell phone tower or something like that, and they're going to have to bank the airplane and kind of turn hard to avoid doing that. And if you get somebody too slow, now you're having them stall. So let me address that concern head on, because as I'm going to argue, that concern is absolutely, totally addressed by bringing them to this IMC safety speed that is the top of the white arc. And I will defend that in detail in a couple minutes. But the basic idea is, again, you get them slowed down, and that has a couple of big benefits. One, it has benefits on its own for the graveyard spiral situation, although at some level, that's less the reason here, because the scud running situation by definition is somebody who's down at low altitude, and typically we're definitely below 1,000 feet, almost certainly below 1,500 feet AGL. I mean, you don't scud run at 6,000 feet AGL, right? So you're down low. If somebody is down low and they lose bank control, they end up kind of thunking into the ground before they ever get to the high speed, have their oh shit moment and pull the wings off, right? So this becomes an IMC safety speed in the scud running situation, not because we're worried about ripping the wings off type situation, but it's really for other reasons. So let's kind of switch gears a little bit and talk about that. So let me start by going to the Pilot's Handbook of Aeronautical Knowledge again for a second, which is going to be over here, okay? And on the next page after where we left off, we get into radius of turn. Okay, let's just talk about this for a second. Radius of turn. And again, pilot-rated controllers should already know this. This might be a refresher. If the bank angle is held constant, so at some given bank angle, and the airspeed is increased, so you go faster, what happens? Well, the radius of the turn changes, and specifically it increases. A higher airspeed causes the aircraft to travel through a longer arc due to a greater speed. So, for example, an aircraft traveling at 120 is able to turn a full 360-degree circle, or for that matter, a 180 or whatever, in a tighter radius than an aircraft traveling at some double, speed double that. In order to compensate for the increase in airspeed, I'm going to add something here. If you want to keep the turn radius the same, you would have to increase the bank angle. It turns out you'd have to increase it pretty dramatically. The radius of turn, or R, can be computed using a simple formula. The radius of turn is equal to the velocity squared, so there's our old friend v squared that seems to keep popping up its head, divided by 11.26 times the tangent of the bank angle. For those of you who had to go through your commercial pilot training, you recognize that formula. For those who are only private pilot rated, you're wondering why commercial pilots have to know that formula, but that's a smile between us commercial pilots. All right. Anyway, and they give a couple of examples here. So if you were to crunch the numbers, and I'm not going to, I'll trust the FAA to get the math right here. If you crunch the numbers for somebody, okay, with a 30-degree bank angle at 120 knots, the turn radius is going to be 2,215 feet. If you double the speed, you're going to get 4 times the turn radius at the same 30-degree bank angle, and so it goes from 2215 up to 8861, which is 4 times 2215, unless you have to be precise, because they must have left off a couple inches of the turn at 120 knots. All right, we'll forgive the FAA for that one. You get the idea. So the bottom line is, the slower you go, the tighter you turn at any given bank angle. Remember, the part of the problem in the scud running, in terms of the threat when you're scud running, is you're flying along and suddenly you get kind of that, something kind of appears out of the murk. A water tower, the light bulb's attached to a cell phone tower, something like that, maybe a hill, or a 5-story apartment building if you're down particularly low or something like that. And so in that situation, how would you meet that threat? Well, first of all, the pilot is going to have to spot it with his or her for Mark 1 eyeballs. Okay, it's going to take a second. You're going to kind of squint. You're going to lean your head forward like 2 inches, as if that makes any difference when you're doing 100 plus knots and so on. But anyway, that's the natural human inclination. So, you put your head 2 inches forward, you squint a little bit, and you're like, oh my, and you realize you've got to turn. And yeah, you have to. I'd really rather you not, start turning quickly when you're in these VFR-in-IMC situations, because I don't want you to go thunk into the ground, but at some level you have to address the immediate threat to loss of life, so you have no choice. Okay, here's the thing. The faster you going, the less time you have before you come up on it. So I'm going to show you, or let's think about it this way. Let's suppose, for sake of discussion, that you can start to make something out a half mile in front of you, just to use a quick mathematical example. So you can start to make out those light bulbs on the cell phone tower a half mile away. Okay, in this murky visibility situation. If you're doing, let's say, 120 knots, okay, that's 2 miles a minute, so you have 15 seconds until you hit the cell phone tower in this particular hypothetical. If you back the airplane down to 90 knots instead, you're doing 1.5 miles a minute, so you go from 15 to 20 seconds. And that might not seem like much, but that's an extra 5 seconds to lean your head forward, kind of squint, kind of realize, and go, ooh, and start your turn. So first of all, by slowing down, you have more time to see the threat in the first place, okay? Your roll rate is going to be essentially the same, because pilots are going to maneuver and the roll rate is not going to matter. Technically, you'll roll a bit faster at the higher speed, but it's not enough to make any meaningful difference. And then you've got your bank angle, and now you have to start the turn. Now, I can't vouch for how much a pilot might turn. Maybe they bank 30 degrees, maybe 45, maybe 60 or whatever. I really do not want pilots to be banking at 60 degrees. I mean, at that point, you're starting to go from the frying pan into the fire type thing, right? So I'd like them to be able to kind of turn tight at some given radius, more by slowing the speed down and so on. But we also don't want to slow down so much so that they stall. So let's switch gears a little bit, and we're going to leverage a tragedy that happened back in 2006, also in New York City. Some of you may be familiar with the plane crash that killed New York Yankees pitcher Corey Lytle. Wikipedia article says Lytle was killed when the small aircraft he owned crashed into a residential building in New York City. It was a Cirrus SR-20. If you go to the death part of it, it says on October 11, 2006, Lytle and his co-pilot / flight instructor were flying a Cirrus SR-20. It crashed into some apartments, okay, on New York's Upper East Side, killing them both. What it was doing, they were going northbound up the East River past the Queensboro Bridge, and there's restricted airspace up there. By the way, Wikipedia, this is... That's wrong, but that's a Wikipedia thing. Let's just address it. It says a strong wind from the east due to an incoming front caused the plane to be blown into the building as it was making a 180-degree turn. So I have nothing to do with editing this page, but whoever wrote it, people who read this, they're going to think that, okay, poor pilot, poor Corey, poor Tyler, they were doing a 180-degree turn, and suddenly they get this big, strong wind gust from the east because of an incoming weather front. It was beyond their controls and just tragically out of their control. They were blown into this apartment building. That is not what happened. That's a Wikipedia thing, and so on. Okay, you can go to the article here about this, and you can see they crashed into the upper stories of an apartment building and so on. But let's dig into this a little bit. First of all, I want to note that the NTSB investigated this one a little more thoroughly than most are, partly because this was a New York Yankees pitcher, partly because this was an upper level, story crash in New York City, which has had its share of 9/11 type stuff go on, to put it that way. And so this got, in effect, more attention from the NTSB than they could possibly devote to every single one. And that's why I want to look at it here. So emphatically, this was VMC. This was not a VFR-in-IMC scud running situation. But at some level, what happened was they were trying to do a turn at low altitude, okay, and what they hit was an obstacle. So the principles that the NTSB very thoroughly explored in this accident, even though it's a different setup than what we're looking at, can be directly applied in many ways to the particular scud running type situation and its relevance to what speed to fly. Okay, and so let's go and look at a little bit about what the NTSB did about this particular thing. So first of all, if you pull up the NTSB final report for 929 Charlie Delta, this accident, you'll notice that they say they actually did a full aviation accident brief rather than just kind of the typical stuff they do, and it's because it was high profile. And again, it's not just because the owner of the airplane was a famous, sports celebrity. He wasn't the most famous pitcher ever, but he certainly wasn't the most obscure. It's also just because of the circumstances of it being New York City and so on. So rather than do what I might typically do and look at a final report, I'm actually going to look briefly at the accident brief and so on. If you were to go through this, and I'm not going to go through it in particular detail, you're welcome to, of course, but they took off from Teterboro, they went down the Hudson, kind of took a look at the Statue of Liberty, they went up the East River, and as they were coming up the East River and they were focusing on having to deal with some restricted airspace up right next to LaGuardia, what they were trying to do was a quick left 180 and go back down the East River and so on. So that was the plan. Basically, they didn't make the 180-degree turn tight enough based on their starting position, and yes, there was a wind from the east and so on. Okay, and when they in effect overshot what they were hoping to do for the ground track of their turn, they went into some of the upper stories at 300 feet above street level basically and hit the apartment building. So this is going to go through quite a bit of detail here about the things, including with the fact that because the wind was from the east at 13 knots, they did not avail themselves, as it were, of the full width of the river. Okay, so instead of like getting as far to the east as they could have before starting the turn, or perhaps getting as far to the west as they could, and that way the turn would be into the wind and they wouldn't have as large a radius of turn. Nonetheless, even though their starting point was in effect not ideal, and even though the wind was kind of against them, at some level what I'm concerned with is some of the technical discussions that the NTSB went through based on the rate of turn as a function of speed. And so to do that, I actually want to look at one of the very specific things that they did as part of this. The NTSB, for this accident, commissioned an aircraft performance study. It was performed by a PhD researcher with the Vehicle Performance Division of the National Transportation Safety Board named Kevin, and I hope I'm pronouncing his last name right, Renzi. Okay, but one of the things that was done by Dr. Renzi was a whole series of charts, and I want to focus on this one. Okay, now this one is a calculated Cirrus SR20 bank angle to complete a steady level turn, okay, 180-degree turn, sorry. Some basic assumptions of what the coefficient of lift max would be, what the weight was, what the stall speed is, and so on. Let's kind of unpack this, and I know that this was being used for this particular accident, okay, but let's try to apply it to what we're talking about here. So the stall speed for this particular airplane, zero bank flaps up, was 67 knots, and that's why the line that's governed by these black triangles comes down to 67 knots. At higher and higher speeds, okay, the stall speed is going to, so I mean there's a stall speed for every airspeed because you can stall the wing at any airspeed, so that's the critical angle attack. That's as much lift as you can make. And then these various color lines you can tell from here. So this line, I don't know what color that is, it's kind of yellowish. I flunked out of the Crayola color scheme at about the 8 crayon limit. I certainly never made it to the 64 box, but this kind of yellowish line, okay, is for a 2,400 foot turn diameter, so that'd be a 1,200 foot radius because I did make it to that point of the geometry class. Okay, and then as you go up the scale here, I know that one's red because I got that Crayola down. That's the 1,000 foot turn diameter. So let's just think about this for a second. So let's suppose for the sake of discussion that you're doing 110 knots, okay? If you bank at, just eyeballing it, looks like about 42 degrees, 110 knots, 42 degree bank, and this assumes no wind, you could make a turn with a 2,400 foot turn diameter, 1,200 foot radius. If you bank further and further up to 65 degree bank angle, you can shrink that from 2,400 feet down to 1,000 foot. That's a 500 foot radius. That's a real tight turn. 110 knots, 65 degrees bank. ballpark math, because 68-degree bank, you're pulling 2 Gs. So 110 knots, you're pulling somewhere, I don't have the exact calculations here, I'm just doing this in my head, but you're somewhere, up about, 2.3-ish Gs of pull, and you're really close to flirting with the stall, but you could just get it turned, okay, with a 500-foot radius, 1,000-foot diameter. However, let's say you slow down to something like 95 knots. Well, to do the 2,400-foot diameter, you only need 33 degrees of bank, okay, and you could also flirt with the stall and get the 1,000-foot diameter, 50-foot radius at only 58 degrees or so of bank, and I'm saying only 58 because you still got a decent pull, but there you're somewhere about 1.9 Gs, okay. But there's a different way that I want to kind of look at this. So I assume that somebody's flying along in the soup in one of these scud running situations. They realize there's a cell phone tower with light bulbs attached to it or something like that up ahead of them. And again, as I said, you have more time to react at something like 90 knots than you would at 120. Again, I'm interested in the principle about slowing down before making turns. I'm not per se interested in the exact speeds, but we'll use this one as our kind of baseline. I think what happens is when you spot that cell phone tower appearing out of the murk, okay, and you kind of squint, lean your head forward, you realize, oh shit, and you start to make your turn. I think what the pilot is doing, they're not thinking in terms of this graph per se, but what they're going to do is they're going to bank some amount. It might be 30 degrees, okay, it might be like 45. I hope they're not thinking of banking at 60 degrees. I do not want people scud running doing these 60-degree 2G turns at any speed. That's just, even if if you're slow, you stall. If you're faster, you're not stalled. The faster you go, the bigger the turn. But I don't want people doing 60-degree 2G turns anyway in scud running. That strikes me as darn near suicidal, very high risk type of things. Put 5 bullets before you play Russian roulette kind of stuff. So what I'm thinking is more in terms of realistically, what's a pilot going to do in a scud running situation? They might just bank to about 30 because that is for a lot of pilots about the most that they use in normal flight. Maybe they go to about 45, and so effectively what I'm doing is kind of reappropriating this chart to kind of picture what pilots will do in this kind of situation. So let's kind of play 30 and 45 as 2 examples of what pilots might limit themselves to arbitrarily, okay? And here's what happens. Again, if you limit yourself to 30 degrees of bank, and let's just suppose for the sake of discussion that you're at 120 knots, well, 30 degrees of bank, 120 knots, your turn radius, it's not labeled by Dr. Renzi, but I'm guessing it's something on the order of 3,600-foot diameter. Again, don't quote me on that exact number. I'm just eyeballing it here. You get the idea. If instead you've slowed to what I'm kind of loosely calling the top of the white arc speed, in a Cirrus SR-20, that's 104 knots for the older ones, okay? You back down to, it's still a bigger turn rate, it's still a big turn rate, but it's certainly less than it was here if Dr. Renzi had continued to plot lines on this chart. For the sake of discussion, let's say that they had slowed to 90, because again, we're interested in the principles, not the exact speeds per se. 30 degrees bank, 90 knots. Now you have just over a 2,400-foot turn diameter. Let's call it about, ballpark 2,500. You get the idea. Okay. Instead, what if our pilot in the scud running situation makes out that cell phone tower appearing out of the murk and kind of says, intuitively, 45-degree bank, give it about 1.4 Gs a pull, sort of intuitively. Well, at 120 knots and 45 degrees, you're looking at, again, 2,500-foot turn diameter, so 1,250 radius and so on. Okay, if they're at 90 knots, because we got them to slow down, 90 knots, 45, we're looking at right about 1,400-foot diameter. It's a significantly tighter turn, and because the turn radius, or turn diameter, whichever you prefer, is smaller across the ground, that's how you actually avoid that cell phone tower with light bulbs attached to it that you were able to kind of see out of the muck. So slowing a pilot down absolutely helps, although I'm not going to vouch for the exact numbers for any given situation, and there can be wind that's going to affect the actual turn radius across the ground. But the principle holds. The slower you go, the tighter you turn at any given bank angle. And for what it's worth, I think for most pilots in that kind of situation, 45 is about the most bank angle they would intuitively go to. I think you have problems if you go above that anyway. And If we think about this for a second as kind of a function of the stall speed, where we're worried about stall, I still think we're going to be somewhat north of this at the top of the white arc, but let's think about this for a second. Stall speed is 67 knots, okay? 67. So you would stall at about 80 knots. If you think in terms of what I'm looking at doing for proposing for the IMC safety speed, I'm thinking of something up in here. If you were to crunch the numbers, that stall at 45-degree bank angle would be right about here. And in fact, I hadn't planned on doing this, but I don't see any reason not to do it. Let's do it for the 172S. And let me go to, very quickly, it'll be in section 5. Pardon me, I hadn't planned on this, so it'll take me a second to get to it. But the stall speeds, and now I'm worried about, say, the stall speed at a 45-degree bank angle with the flaps up, okay? We're looking at it going from 53 calibrated up to 63 calibrated. Even for the Cirrus SR-22 that's currently being produced. So this will be a faster airplane. And I went past it because I was going too fast. Let me just try to grab it real quick. Thank you for your patience while I try to find it. There we go. Stall speed. This is even at max gross weight. Stall speed with the flaps up, 0-degree bank angle. And on the Cirrus, the most forward CG stall speeds will be faster than the most aft CG stall speeds because you have to have greater download on the horizontal stabilizer to balance the forward CG. So it goes from 74 indicated, 73 calibrated at 0 bank up to about 87, okay, for both of those there. But so I'm still talking about 104. Okay, so again, that takes you up to 87. For this airplane, I'm still thinking in terms of about 104, 110, which is the top of the white arc for the current SR-22 is 110. Let me get my bearings a second. Okay, nope, that's not what I wanted. Sorry, I hadn't planned on going to that, and that's why I kind of had to think about where I was for a second. All right. The bottom line is I want to have pilots slow to that top of the white arc speed. That helps, and I still think that for any kind of reasonable bank angle they might use to swerve around an object, and I really hope they're not doing that in the first place, it still provides a buffer against the stall. Let me express the same thing a different way and sort of switch gears a little bit. So let me go to YouTube, and we're not going to play any videos here, but I will note if you search for something like Flight Chops, Dan Grider, this is at least on the day I'm filming this, the kind of things you get here. I suspect some of you have seen Steve's Flight Chops channel. Flight Chops is an extremely popular channel by this guy who's based out of Toronto named Steve. This particular one was filmed ballpark a year ago with a flight instructor from the Atlanta area named Dan Grider. Dan Grider has actually gotten a fair amount of attention in the last years in a variety of ways. I'm not going to click on this particular one. I will note that he's gotten enough attention that he's gotten attention for several reasons. The guy is very passionate about general aviation safety, and he's proposing a number of new concepts that I think are absolutely wonderful. There's a series of videos that have been done on other channels about his ideas. I'm not here to engage with his ideas particularly. I will note one particular idea that I want to focus on, and the way I'm going to do it is by going to this one. Also a Flight Chops video with almost 250,000 views 10 months ago, so a little bit after. And I'm not going to play the video, but I will come down to a couple things. First of all, let me hit show more. And there's a disclaimer there. My apologies, I lost my bearings. The thing I actually wanted in the notes is from the more in the first one. Okay, so this actually gives you some sense of what is covered in the video. But one of the things that Dan has been floating for the last year or so that has gotten a lot of attention is this idea of DMMS, design minimum, notice minimum, but design minimum maneuvering speed. What Dan's doing in short is he's taking a principle that the airlines use to help with their safety record and trying to apply it to general aviation. And that's why he's talking, for example, or the notes here are talking about the airliner methods, okay, using that to solve general aviation problems. Now, for other reasons, Dan is floating this idea of the DMMS, the design minimum maneuvering speed, as a minimum speed at which to maneuver the airplane. He uses it for a variety of reasons. It is defined, for reasons I'm not going to get into, as VS1, or that's the stall speed with the flaps up. But the stall speed times what's essentially 1.4. The 1.404 adds like a tenth of a knot for most typical airplanes, so I don't even really care. It's basically 140% of the stall speed. Let's think about that for a second. 140% of the stall speed. If you think of that in terms of what I'm proposing here, if the stall speed is 50, 140% of that is 70, and that's really about the slowest you would ever see the top of the white arc. So even though my proposed IMC safety speed can fluctuate, and even though it has absolutely nothing to do with Dan Greider's concept of the DMMS, it turns out that my speed that I'm proposing is, for other reasons, Dan's DMMS speed or a little bit higher. Now, if you were to get your head around, and you're of course welcome to view the full video and so on, of why Dan is talking about that speed, he is basically going to say something like, so this is paraphrasing in my own words, any normal reasonable bank angle you can maneuver and you're not going to stall the airplane at or above that speed. Well, my proposed speed is that or higher, and so you are not going to stall the airplane at anything like a normal bank angle. Now, if you go to 80 degrees bank angle and you pull back on the elevator, or by the way, if you go to any bank angle, including 0, and just haul back on the elevator, you're going to stall, because that's what a stall is. But for all intents and purposes, related to bank angle and then whatever pull is necessary to maintain level flight, my speed is basically Dan Greider's speed or a little bit higher. Okay. One other thing on this second video that I did want to cover, I thought that the notes were in the... Okay, if you actually look at the public comments, it turns out that a comment that I made when this video came out is the very top comment. Now, it's possible that's just because this is my account logged in, or it was, I'm on the local safety council for ZID right now. But anyway, you'll also notice this one was pinned really to the top by Flight Shop. So if you go and search for this yourself, this should be the top public comment that you see, because Steve, who runs the channel, okay, pinned it himself. He put in this little thing, say, hey, Dean, I like your ideas. It got several replies, got a whole bunch of likes and so on. Let me just note this. This is a somewhat related or unrelated thing to DMMS. So I just put in a quick note, hey, as a flight instructor and controller who's already involved in trying to improve ATC training about emergencies, I think that this particular video is excellent. So pilots, do not forget, you're the PIC, and if you need help, please do not hesitate to declare an emergency. And that's especially true when you get into these murky, like VFR, and it's kind of marginal VFR. Is it IMC? Is it not IMC? And so what I advocate is once you get in these situations and it starts to become unsafe, please do not be afraid to say unable to a controller if we start doing too much too fast, and declaring Mayday emergency and so on like that. And if you actually look at the replies, there were a number of replies, including from Dan, saying absolutely yes, sir. I've got other comments from that. And one I'll just note, I don't know where this went, although I suspect if this was starting to happen, it might have been affected by COVID, because this video came out just before COVID started. But Dan Greider, the guy that we're talking about here, said he got numerous calls and private messages in the last couple of days from managers at U.S. Center facilities. I'm actually a little surprised if that's really true. But anyway, I think he might just mean ATC facilities, that thanked us for doing this drill and including this ATC aspect. They are using this video as content for in-house future staff meetings. The positive, constructive conversations that it has started has been profound. And I think that an invitation is underway for Flight Chops, Steve from Toronto, to speak to an AC managers group. Now, I don't know if that happened, and if it didn't, it might be that it was affected by COVID, because again, this thing came out like just before COVID hit and so on. But the point is, I'm aware of Dan's maneuvering speed. It is definitely getting traction within the community. And if you were to go through other videos where you see Dan Greider, including talking with somebody I am not related to, though his last name is the same as mine, named Juan Brown, who runs the Blanco Lirio channel, an excellent, fantastic aviation safety channel, by the way. In this particular video, and I'm not going to click on it, but Juan and Dan are talking about several things, including the DMMS and so on. But the reason I'm bringing this up is because, and let me go back to this for a second. If you think about 67 knots times 1.4, that's going to take you, I believe, to about 93, 94 knots, if the math in my head is correct. And that's basically Dan's design maneuvering speed for this particular airplane. Again, the top of the white arc's about 104, 110, depending on how recently the Cirrus that you're flying was built and so on. So we're still just a little bit north. But the bottom line is, for all situations, what I advocate is There are benefits by slowing down to what's essentially the top of the wide arc speed. That does not mean putting flaps down. And depending on which situation that we're in, we either get to it fairly quickly, we get to it maybe relatively quickly, you know, we wait a couple minutes but then start packing somebody down, even though it's sort of for different reasons, but it has benefits about the turn radius, and we are not slowing them down too slow. Or in these situations, when time becomes available, then we get them back down to it, but that's not really our first priority. And all of that is in accordance with absolutely the spirit of what is talked about in 10-2-9 of the .65 about getting the airplane slowed down when we can. I would love to do it in VFR conditions if those are available, but if not, we can still responsibly slow them down to a safer speed when we can. So that's kind of the advanced discussion about the IMC safety speed. Thank you very much.